Welcome to science class. Today we are going to learn about minerals. And so this begins our study of the geosphere, the solid body of Earth. Matter has certain properties, and those properties are reflected in minerals, which are the building blocks of Earth's lithosphere. This is most notable in the wonderful crystal geometry that minerals possess. This crystal geometry is completely dependent on how the elements which make up a particular mineral bond together. Sulfur and iron atoms will crystallize into pyrite and form these beautiful golden cubes. Meanwhile, sulfur and lead atoms crystallize into galena, which also forms cubes, but it has very different properties. That's the nature of matter. When specific atoms combine in specific ratios, they form special compounds. Water is always H2O, and nothing else is. Galena is always PBS, and nothing else is. What we are going to learn in this video is what minerals are and the natural processes that form them. Let's get started. I want you to guess what the most common element in Earth's lithosphere is. In the first Earth science video, I told you iron is the most common element in Earth, but almost all of it is in the core. So imagine you're walking on a bare rock formation. What element is primarily under your feet? It's actually oxygen. Almost 50% of the lithosphere is oxygen, followed by silicon. Aluminum and iron come next. Then calcium, sodium, potassium, magnesium, titanium, and hydrogen round out the top 10. But nowhere on Earth will you be able to find any of those things in a pure elemental form. They always form solid compounds, which we call minerals. Minerals are naturally occurring solid chemical compounds. Almost all of the solid stuff that isn't living or man-made on our planet is some kind of mineral or is composed of minerals. Most minerals, but not all, have a crystalline structure, and most, but not all, are inorganic. They form under geological or hydrological processes, and not through living organisms. All materials, regardless, have a definite chemical composition. That is, we know exactly what they're made of and in what proportions. Water, for example, is always 2 hydrogens and 1 oxygen. If you add another oxygen, it becomes hydrogen peroxide, which is a completely different substance, but it's not a mineral. Rhodochrosite, which is a very pretty mineral, forms from manganese, calcium, and oxygen in a 1:1:3 ratio. If you substitute the calcium atom for a silicon atom, well, that's the mineral rhodonite. There are vast numbers of different minerals, somewhere between 4,500 to 5,500. Many of these varieties are just variations of the same mineral. Amethyst, citrine, and ametrine are just slight variations of quartz. But I don't want to get into that yet. First, I want to cover how minerals are formed and why that information is useful. The most common way that minerals form is by crystallization from magma. Magma is nothing but melted minerals, and when magma cools, the atoms in the material crystallize with each other to form different minerals. We call the material minerals formed from the parent body or parent material. Minerals that form from magma tend to be incredibly durable and hard because they were created under such extreme conditions. And these specific minerals can't form under any other process other than crystallizing from magma. If you take all the raw ingredients that form a certain mineral like quartz that crystallizes from magma, grind it up, dissolve it in water, and let it sit, it will not crystallize into quartz. It will only do so if it crystallizes from magma. Next are precipitation reactions. Minerals that form this way form directly out of water. The raw ingredients that make these minerals are in solution, which means they are dissolved in water. The minerals form as the water evaporates away, or they form within the water itself. You can replicate precipitation by dissolving salt into water, pouring it onto a flat surface, and letting it sit for a while. Some precipitate minerals can form right on the surface, such as halite. Others form underground and require very hot water. The geyser fields of Yellowstone National Park are a wonderful place to see this kind of thing happening. At the edges of hot springs, you'll see colors and shapes and piles indicative of the minerals that form there. Some of the coloration, however, is a result of living things, swarms of extremophile bacteria and archaea. The coloration, for example, in the Grand Prismatic Spring is actually due to different chlorophyll inside of those organisms. Probably the most incredible display of mineral formation is the giant crystal cave in Nica, Mexico. These crystals of gypsum were formed when the cave was flooded. Deep below the surface, the cave is well over 200 meters below ground. The heat from nearby magma reservoirs heats the water, giving it the necessary energy to bond together the elements that make up the gypsum crystals. Minerals can undergo metamorphosis as well, and we call this process of mineral formation heat and pressure. Pre-existing minerals, when subjected to incredible pressure and temperature deep within the earth, can completely rearrange, forming 1, 2, or maybe even 3 new minerals in the process. For example, garnets and diamonds form under these conditions. Garnets, for example, can only be found in metamorphic rock formations, and they're made when pre-existing minerals recrystallize into a new form. Diamonds are formed when pre-existing carbon rearranges into a new form. And then finally, there's hydrothermal solution. This process involves water depositing minerals within existing rock structures. This is different from precipitation, because in precipitation, the minerals form directly within the water solution, whereas in this case, water delivers minerals and puts them into rock formations. This is how ores are formed. Water dissolves weaker minerals away, and then it picks up metals like copper, lead, gold, silver, platinum, zinc, and then that superheated water naturally rises up through faults or cracks within rock structures. Eventually that water cools down, and the metals it was carrying get deposited into the rock in structures called veins. Those metals react with already pre-existing minerals within the rock and form new minerals. As I stated earlier, a compound generally has to be 4 things to be considered a mineral. It has to be solid at room temperature, possess a crystalline structure, have a definite chemical composition, and be inorganic. But it's not always that simple. For example, glucose, that should be a mineral. It has a definite chemical composition, it's solid, it forms crystals, but sugar is produced from sugar cane. It's organic. What about opal? Opal has the exact same chemical makeup as quartz, but it doesn't form crystals. So does that count as a mineral? Our bodies form uric acid crystals, which can cause kidney stones. The shells of snails and the bones in your body have calcium carbonate and other minerals in them. So are they really minerals? What about snowflakes? They form naturally, produce crystals, have a definite chemical composition. There's a term called mineraloids that we use for certain types of substances. They're not quite minerals, but they fit most of the made-up rules we came up with for minerals. So now that we've been talking about minerals for a while, we can ask the question, who cares? Well, you should, and not just because you're in this class. You should at least appreciate minerals. And not just because some of them are beautiful, but they make modern life possible. Without minerals, we can't build anything. Without understanding the properties that certain minerals have, we can't improve the things we build. Better batteries, safer, stronger materials, more efficient cars, and countless gadgets depend on the mineral riches our planet contains. I, for one, like technology, and I especially like new technology. A big difference between the creature comforts that we have today versus the much fewer creature comforts people had only 50 years ago, in large part, is thanks to minerals. We can also use minerals to understand geological formations and Earth's history. If you've ever hiked in a place rich in granite, such as this, you may have noticed what almost looks like glitter on the ground or on your hiking boots. In fact, this is a mineral called muscovite. Muscovite is a really interesting mineral because it breaks off in flat sheets. In Moscow, where the name muscovite comes from, this material was used long ago as window panes. This chunk of earth is actually many different minerals combined together, and one of the minerals on here is muscovite. If you look very closely right here, you can see that there are multiple layers, and I can actually peel those layers off. Muscovite only forms at temperatures around 900 degrees Celsius. So how did it get that hot on the surface where we find the muscovite? Well, it didn't. The muscovite and the entire surrounding granite landscape formed many kilometers below the ground, millions of years ago. Later, the uplift of the lithosphere through plate tectonics and erosion of the layers above it revealed these wonderful landscapes to us and many others. I love nature. It's beautiful. And I find nature even more beautiful when I can look at nature and understand how it got that way. Hopefully that same appreciation passes on to you. That should just about do it for minerals, at least for now. Next time, we are going to learn the different mineral groups, the properties of minerals, and how to identify a mineral. Thanks for watching.